Hello, everyone. In this lesson, I wish to go over some simpler examples. Okay, we do have recordings on other examples that involve logarithm functions and trig functions, etc., and rational functions. And in this recording, I wish to just go over some simpler examples, which you should know how to do it and also I will give you some alternative methods to test positive and negative, okay, from your algebra experience. So first of all, in this section, in this part, we want you to be able to understand absolute max, absolute min. So I put these flashcard contents on here, okay? And these are the contents that you should refer to frequently, okay? And the flashcards will be available to you during the quiz or during final exams. So you just use them, but you certainly need to know how to proceed with these questions and when do you need what. All right, so with that introduction, let me take one of the questions from homework, right? So this one I'm going to take, this is number 10. Well, it's even number question. And number 2, that it's simple enough, it's comparable with number 9. So we're going to do number 10 in this first example. Okay, so we have f of x equals to 2 times x raised to the power 3. Okay, I'm going to talk about what we're going to do about it. Okay, so 9 times x squared plus 12x subtract 3. Okay, so for this question, we're going to find the interval of increasing, decreasing, and we're going to find local max, local min, and we're also going to find concavity and inflection points. So along the way, we're going to use all of these concepts. We're going to use all of these concepts. All right. So now I'm going to put away. I'm going to make the screen a bit larger on our working area. Okay. So now we look at what we want to do. Oh, okay. Hold on. Okay. We're going to find the intervals increasing, decreasing, local max, local min, and all of these. Okay. So we'll come back to it when we need. All right. Okay. So now in this case, obviously we're not given a closed interval. So extreme value theorem does not apply. Okay, extreme value theorem only applies to when the interval is closed and the function is continuous, right? So in this case, it doesn't apply. However, definition on absolute max, absolute min, local max, local min, Fermat theorem, so closed interval test doesn't apply. Definition about, you should have all of these flashcards with you, okay? Second derivative test, first derivative test, they all apply. So we're gonna go over them in this example. Okay, so first we're gonna find intervals of increasing and decreasing. Okay, for all of these, we need to know critical number. We do, because those are the places where the derivative changes sign, right? So naturally, we're going to look for critical numbers. So first thing first, okay, before we do anything, is that we're going to find critical number. Okay, so we're going to first we're going to find critical number. Okay, or critical values. What's the definition of critical numbers, right? We have studied Fermat theorem, right? Fermat theorem established the relationship between local max, local min, and a critical number. And of course, we have a definition of critical numbers. The definition of critical numbers is that first of all, it has to be in the domain. And secondly, either the derivative is 0 or the derivative doesn't exist. But what do we have here? We have a polynomial. Polynomial is continuous and differentiable for as many times as you want, right? So the critical number definition in our case, the derivative does not exist case it will not apply here. We will only have critical numbers that is the first order derivative equals to 0. Okay, all right. And of course, we know that critical numbers are candidates for local max and local min. Okay, so from that understanding, we're going to find the derivative, right? Derivative of this function, we get 6 times x squared minus 18x plus 12. Okay, we double check 6x squared minus 18x plus 12. We absolutely need a factored form. Why we need a factored form? Because we need to find critical numbers, right? Because next step, we're going to set the derivative equals to 0. So you can do the factored form later or now, right? So we're going to factor out the 6. Okay, so this part is algebra. This part is algebra. So we got x squared minus 6x plus 2. Oh, wait, 3x. Okay, and you double check if I will go back to the previous step, right? It does. Okay, and that can be factored. You can factor any way you want, right? That equals to 6 times x minus 1 times x minus 2. And here we go. So when we set the derivative equals to 0, right? So this is the step where you're going to go. We set derivative equal to 0. So if the derivative equals 0, then we get critical numbers. You can number them any way you wish. Okay, you can call them x equals to x equals to 1, x equals to 2, or you can call them C, right? C is the first letter, or it's all up to you. But be consistent. Be consistent, okay? Be consistent with yourself. If you want to use C1, C2, that's okay. So C1 is critical number 1 and critical number 2. You don't have to have you know, both, right? Because you don't want to confuse yourself. You don't want to confuse yourself. So we just got critical numbers. You call them x1 equals to 1, x2 equals to whatever. Okay, so this is optional. This part is optional. Okay, it's too much. Sometimes redundancy is just as long as you know there are critical numbers, that's fine. So now we know that the derivative changes sign. The derivative changes sign, right? And there are 2 critical numbers. We also know that this is a parabola. This is a parabola. From our algebra experience, right? From our algebra experience, you can attach a 6. Why I do not attach a 6? Because it doesn't change the sign, okay? So you can, right? You can do that and say, okay, this is a parabola, right? This is a parabola and equals to that, right? From our algebra experience, we know that this derivative, if we graphed it, right? If we graphed it, then yeah, surely I don't allow you to use a calculator, but you should be able to sketch it. Okay, you should be able to sketch it, something like this. I have the convenience to use the software, and but you can sketch it without having to use a software. Okay, so that should not be a problem. If you have issues, then please let me know. Okay, so I'm going to just give you a little picture to refer to. This is a different method to the method I use in my other recordings. Okay, so give you multiple methods to do one thing. This turned out to be actually this method is easier, make things easier. Okay, so you can see from this picture, right? From this picture, and let me make some adjustments. I'm making some adjustments so that picture can be better seen. But this is the picture about the derivative. Okay, this is the picture that's about derivative. Let me make it just even smaller. Okay, so how about 3? Okay, you don't have to know how to use this software. Okay, don't worry about that. And so that's better. Okay, so for this picture, what I really, so remember, this is a picture of the derivative of the function, right? And knowing this is a derivative, so we can tell from this picture. Okay, so I'm going to annotate. There's a x-intercept, the x-intercept, right? And there are 2 points x-intercept, 1, 0, 2, 0. So this point is 1, 0, 2, 0. So we have 2 x-intercepts, and those happen to be the critical numbers, right? You can see that relationship. And secondly, and if you want to see the sign change, if we want to know the sign change, right, you will see that the derivative is positive on this piece, right? To the left of 1 and to the right of 2, and the derivative is negative between 1 and 2. Okay, I hope you guys see that. And now, with that understanding, okay, so let me mark these 2 points. These 2 points are, okay, 1, 0, 2, 0. Okay, so 1 and 2 are critical numbers, right? So I'm going to put a circle for them. So that's the picture. So we basically know, I'm going to draw the following picture to make it, make it easier for you to see, right? So for the derivative, okay, so we have come to the point so this is a number line, right? There's a point which is 1, and there's a point that is 2, okay? We don't need this long. And from this picture, you can tell, right? You can tell the derivative at less than 1 to this side, right? The curve is positive. That means the derivative is a positive here, right? At 1 is 0. That's a critical number. Between 1 and 2 is negative. Whoops. Okay, I need to change the mode. Okay, it's negative. At 2 is 0. Okay, so this is 0. Let me change the color to be more consistent. And of course, we're gonna have to make some adjustment here. So I think you got the point, right? I will tell you how to draw work. Right now, I'm just explaining to you why I'm doing these things, And so between 1 and 2, the derivative is negative, right? Derivative is negative. And then after 2 is going to be positive. Positive. So we know the sign of the derivative. And next, it's about the function. It's about the function. We know that, right? If the derivative is positive, then it's increasing. So for function, so okay, if I draw the same number line right here, right? Remove that. And then you can see this interval. Okay, hold on. You can see this interval on this interval, right? From negative infinity to 1, this is the interval where the function is increasing, right? F is increasing. And in this interval, the F is what? Decreasing, right? Decreasing, right? And this interval is increasing. All right, so with that understanding, how do we answer this question? How do we answer this question? You can use the method I have shown you in the other, but this seems to be faster and much quicker. Right, so now let's answer this question. I'm going to do some cleanup. Okay, I'm going to do some cleanup. Clear all drawings. Okay, so with this understanding, we're going to answer the first question, which is the interval of increasing and decreasing, right? To answer that question, you're going to say, okay, F is increasing from negative infinity to 1 and the other interval from 2 to positive infinity, right? And you're also going to say F is decreasing in the interval between 1 and 2. So at this point, I like you guys to compare the definition of increasing, decreasing, and increasing, decreasing test. Okay, so let's look at them. Increasing, decreasing test. Increasing, decreasing test right here, right? So that's what we use that for. We use that increasing, decreasing test. All right, now we answer the first question. Next, we want to find local max, and local min. Okay, local max, local min. Local max, local min using first derivative test, right? So let's bring first derivative test. Copy. Okay, I'm going to bring this here. Local max, local min, using first derivative test. Right, we'll put it next to it. We have the picture earlier. We have that picture earlier, right? So you can see we're going to compare word for word. Okay, that's the derivative, right? That's the function, right? In the first derivative test, we just have to apply first derivative test. Okay, what does it say? If f prime changes from positive to negative at c, of course, first c is a critical number. We already found our critical number. 1 and 2 are critical numbers, right? And that's 1. Number 2, if f prime changes from negative to positive at c, right? So we have critical numbers. then you're gonna say x, you can do this actually, because to say it's a critical number, you can just best say f prime of 1 is equal to 0, right? And then you say f, well, wait, f prime, you're going to use the same words. You basically copy the words, okay? So changes from 1, left of 1, right of 1, right? We just need this piece. We just need this piece, okay? So I'm going to copy. I'm going to bring it here. Okay, I'm bringing it here. This is the derivative, right? This is the derivative. And then you're going to just, because that's all we need to say, right? You say f prime changes from positive to negative, right? Oh, I need to copy the positive negative sign there, right? So I'm going to copy this to bring it to our view. Oh, wait. There we go. Right? So that's all the information you need. Then you say f prime changes, right? You copy the word for word, right? At a critical number, f prime changes from positive, you can even use some shorthand notation, to negative, at what? At 1. At 1. You copy word for word at 1. Okay? From positive to negative, from positive to negative, from positive to negative. Therefore, f has a local maximum at C. Okay? Then you say f has local max at what? C is 1. Okay? C is 1. And what is it? What is the value? Okay? Be careful. The derivative at 1 is 0. Derivative changes sign from positive to negative. F has a local max. Okay? So f is no longer the derivative, it's f has local max at 1. So next, you need to show the reader, okay, f of 1, okay, f of 1. What is f of 1? Because at that point, we have local max. Local max. What is that local max? We're going to go back to the function. Okay, we're going to go back to the function. Right there, right? And you plug in the critical number 1 in place of x, in place of x, in place of x, and you calculate. We get 2. So local max, so you tell the reader local max is f of 1 equals to 2. 1 tells where. Okay, where we get local max. And 2 is what? What is the maximum value of the function? In other words, if you see this as a function, right? There's the input. The input is x, right? The output is f of x, right? So when input equals to 1, the function reaches its maximum, which is 2. So that's the, but of course, this is just showing you how to, what it means, okay, combining with the definition. At the end of it, I will show you how to show your work, okay, how to show your work. So we have done that for 1, and we're gonna do that for 2, okay? So at 2, what happens? Well, at 2, f prime changes from negative to positive. Okay, from negative to positive. So we're going to repeat that, right? Repeat that, but this time we're going to have a local minimum. And then you're going to do similar things, right? F prime of 2 is equal to 0. This is just to demonstrate that 2 is a critical number. And f prime, right, the derivative changes from negative to positive, because you see in the neighborhood of 2, right, in the neighborhood of 2, we change from negative to positive. Okay, so then we say by first derivative test, f, okay, f has local minimum at what? At 2. Okay, at 2. So when you apply the theorem, you don't say C anymore, because now we have a value for C, right? So you use that C. And what is the local minimum? So we're going to go back to the function again, right? And we plug in the critical number into this function for the local minimum. Okay, so that's going to be local minimum at 2. So replace x by 2. Replace x by 2. Okay, so then you do your calculation. So let's see what is the local minimum. It's 1. Once again, same idea, right? Same idea. You don't need to show this part. Okay, I'll have a closure for you. So when x equals to 2, right? So f of 2 equals to 1. So this is a local minimum. This is local minimum. Okay? So now, the next question is that we want to find the concavity. Concavity. For concavity, we will need to take second order derivative to apply second concavity test, and also find inflection point, right? So we just did first derivative, right? First derivative test. And next we're going to do concavity test. Definition and concavity test, okay? And so we have these definitions about concave up, concave down, right? And we also have a concavity test. In the end, I will show you how to do second derivative test on the same question, Okay, so I will give you different versions of this question. But anyway, so let's look at how do we determine concavity, okay, using concavity test. Well, we're going to go back to the function. We'll go back to the function. And we already have a first derivative, second derivative, right? So we already have first order derivative, right? We have second order, we have first order derivative. We just have to find second order derivative. So I'm copying all of these here, copy and paste here, but I really don't need all of this. I don't really need all of this. I don't need this, right? I don't need this. And I just need to know second derivative, first derivative. So I'm going to bring all of these here. Okay, the function itself. So next we want to find out is that we're gonna study concavity. Concavity. We have the function, we have the first derivative, and we just need second order derivative. Second order derivative. Okay, second order derivative is a derivative of the first order derivative. So we're going to differentiate the first order derivative. So you get 12x minus 18. put it in factor form. So we're gonna factor 6 out, and then we get 2x minus 3. And there's certainly sign changes for this function, right? There's certainly sign changes for this function. But it's not very difficult to identify the sign changes for this function because we're about to use a concavity test. Okay, so I'm going to bring concavity test close to us. Okay, concavity test close to us. Right there, right? So we have concavity test right next to us. So we just need to know the sign of second order derivative, right? And when does second order derivative equal to 0? Because before 0, after 0, that's where sign changes, right? So we set second derivative equals to 0. When we set this equal to 0, what we get is we get 2x minus 3 equals 0. And consequentially, x equals to 3/2. 3/2. All right. So this is a straight line. This is a straight line. Okay, you can use a graph. You can use a graph, but you hardly really need it because you just need a number line. You just need a number line, and you have a 2/3 there, right? You have 2/3 there, and 2/3 is. And remember, this is about second derivative. Okay, it's about second derivative. Second, so I have two f2 primes. Okay. Okay. Let's look at the sign change. If you choose a number, if you choose a number smaller than 3/2, smaller than 3/2, and plug in the second order derivative, what you get? Think of you plug in a number smaller than 3/2, say 1, all right, 2. No, not 2. Think of 0. 0 is less than 3/2. You're gonna get negative sign. Second derivative is gonna be negative, right? At 3/2, second derivative is gonna be 0, right? It's gonna be 0. And if you pick a number larger than 3/2, say 2 or 5, your second derivative is gonna be positive. And what does this tell us about the function? It tells us about the function, right? According to concavity test, right? When second derivative is negative, the function is what? The function is concave. Whoops, what did I do? Wait. Okay, so this is a bunch of negative. I'm sorry. Okay. Okay, this is a bunch of negative. I deleted by accident. Okay, I deleted by accident. I'm sorry about that. Okay, so now on this piece, second derivative is negative, and according to concavity test, the function is concave down on this interval. And on this interval, the function is what? Is the concave up. Okay, concave up. That's it. But of course, it's not done. We need to use your word to describe, right? And then you're gonna say, okay, F is concave down in what interval? In the interval from negative infinity all the way to 3/2. So negative infinity to 3/2. Okay? And it's concave up in the interval of from 3/2, 3/2 all the way to positive infinity. So concave up, concave down, right? So concavity question is answered. How about inflection point? Well, at 3/2, right? We have an inflection point, definition of inflection point, right? Let me bring that inflection point definition in front of us. The definition of inflection point. Did I have that? Oh, if I don't, no problem. We can find it. Okay. Second derivative test, inflection point. So this is about concave up, concave down. I need to bring that definition of inflection point. Okay, we have it. We definitely have it. I'm going to find it. Just 1 second. Okay, I'm going to find it. So, hold on. The concavity, the inflection, let me just type it. Okay, inflection points. Okay, inflection point. Inflection point is a point, okay? So an inflection point is where the curve of the function changes from concave up to concave down, or from concave down to concave up. Okay, so I'm going to copy and paste it from concave down to concave up. So there's change of concavity. Okay, so that's inflection point definition. So let's see what happens at 3/2, right? Well, x equals to 3/2, right? At 3/2, we have a change of concavity from concave down to concave up. So 3/2 is a point that is the input point for the function. Okay, so how do we find the point, right? In order to find that point, we have to plug in this number at 3/2 into the original function. Okay, into the original function at 3/2. Okay, so we're going to replace x by 3/2 in all of these cases. In all of these cases. In all of these cases. Right? Compute. So we get 3/2. Wait, actually it doesn't seem to be true, right? So let's make sure we get the calculation right. I'm cheating. Okay, it's a 3/2. It's a 3/2. I guess it is, right? Anyway, if you find any mistake, let me know. Okay, so plug in this number. So now what is the inflection point? Inflection point, right? We know the input of the inflection point is 3/2. So that point has to be a point. So the 3/2 and f of 3/2, right? You plug in, that's the output for the function. So that number happened to be 3/2 comma 3/2. So let's confirm. Let's just to confirm, right? So I'm going to explain what is inflection point, right? So we have the function here. Hold on, sorry. We have the original function here, right? So if we graph it, right? If we graphed it, we're gonna put a nice view. Okay, we're gonna put a nice view here. Okay, so -1, and make this is 3, -5, so make this 10. Okay, and the layout. Okay, so you can look at this curve. Look at this curve, right? According to what we have learned, right? So we have this curve, and we have this is the curve of the function, obviously. Okay, let me just make one more adjustment here. Just like this. Okay, maybe -1, something like that. Okay. To illustrate, right? What do we have done? This is the f function, right? I'm going to bring you f prime. F prime. F prime. Okay. Let me make just a little bit adjustment here. There we go. Wait. There. All right. Okay. And f double prime. Okay, so I'm going to bring these two functions, first derivative, second derivative. Okay, just hold on a second. I'm going to give you a comprehensive interpretation of these and how they're related to what we're doing here. Okay, so you can see from 1 to 2. Okay, I'm going to make some adjustment to this is 1, right? I'm trying to line up. And this is 2. And so I'm lining up this one with this one, 2 and 2. And so you can see 3/2 is right in the middle. 3/2 is right in the middle. So we're good. We're good now, right? Number 9. We don't have to make this too long. So this first derivative, second derivative, right? This is the curve of the function. Okay. Make one more adjustment to the first derivative, and this is negative. All right, now we can see very clearly. You see, between 0 from -infinity to 1, the curve is increasing, right? So we reach the local maximum right here, local maximum here at 1, 2. 1, 2, that's a local maximum, right? And the local minimum at 2. Okay. And so the curve, actually, there's a concavity change at a 3/2. 3/2. Now I'm going to put all the points in place. I'm going to put a point 1, the local max, local min, right? So I'm going to put the points in place, right? Because we found those local max, local min, right? So this is local max, right? Local max. That's a 1, 2, right? 1, 2. Local max. Okay. Local min, 2, 1. Local max, local min, right? Let me adjust the picture just a little bit so you can see it is. Okay, so it is a -1 over here 5. So you can see better, okay? You'll see better. So this is a local max, this is local min, reflected on the critical numbers. They're local max, local min. And there's a 3/2, right? At 3/2, we know that's the inflection point. So I'm going to mark that inflection point right here. I'm going to use a different color. I'm going to use a different color, blue. Okay, maybe not a dot, but a cross. You see that cross, that blue cross. Okay, that's where the change of concavity takes place. A concave down, right? Concave down from negative infinity to 3/2, and concave up. So from this, so 3/2 is the point of dividing concave down and concave up. So that's the point we call inflection point. Inflection point. With all of these interpretations, then you may wonder, how do I answer, how do I show work? Show work, right now, I get to show you how to do the work, how to show work, right? You don't get to, you don't, well, if I don't let you use the calculator, then you won't get the graph, but you can still do it, okay? So how do you get started, right? So what you do is that from the function, right? So I'm going to show you how to show work. Over here, remove this, right? Remove this piece. You don't need that. Okay, the function, first order derivative, and I'm also going to do second order derivative right there. When you organize your work, you have your concept clear, okay? So for your first derivative, okay, for your first order derivative, you will tell the reader, okay, so we first get the critical numbers. You get the critical numbers to answer increasing, decreasing. You don't even have to show this, right? But we have answers earlier. Okay, right here. You're going to show your work right there. You say f is increasing from negative infinity to 1 and 2 to infinity, decreasing from 1 to 2. Okay, the interval of increasing, decreasing. So that's the first important part, right? Because that asks us to give the interval of increasing, decreasing. Second, local max, local min. Local max, local min. You bring that over to here. Okay, so you're going to tell the reader about your local max, local min. Do you need this? No. You don't need that. That's just for your understanding. Okay, local max, local min, done. Concavity, right? So finally, we get to use our second order derivative, concavity. Concavity and the inflection point, okay? I'm copy and paste here, and I'm going to bring it here. Okay, so this part, we have second order derivative done already. right? You don't have to show this picture. And you can just say, if you show that picture, just nobody say you can't, right? So it's concave down in this interval, concave up in that interval. And so up, then the next one is about inflection point. Okay. Inflection point. That's it. So now let's look at everything, all the work you need to show. Okay. So let's see if I can trim some. Okay. 100%. So you can see the whole picture. Okay, now let me make it 150%. Right? Show work. Where's my show work? Show work right there. You have a function, you take first order derivative, second order derivative. You can move this part later. Sorry. You can move this part later. Right? So on your work, you're going to show work. First derivative, put this after. You can put this after, right? You don't have to have that. And you tell increasing, decreasing. And local max, local min, you apply first derivative test. And then concavity, right? You can put your second derivative right there, no problem. And concavity. So overall, right? Just this much, just this much. You can even trim these things. You can trim those things. But I think those are nice work to show. Those are nice work to show. Okay. Second derivative, I would show that part. What is up to you? You don't really need to in this case. That's it. That's it. Now, that's is to determine local max, local min using first derivative test. How about we use second derivative test? Right? So local max, oops. I hit the cap lock, okay? Local max min, second derivative test. Derivative test, right? Suppose I have all these work shown here, right? I have all these work shown here, and I've plotted intervals and everything, but I just want to show work on local max, local min using second derivative test. What do I do? Well, you can do the following. Okay? If I want to do that, of course, you still have to show the increasing, decreasing interval, but on local max, local min part, okay, you will need the second derivative. You will need the second derivative. And what you do, I'm going to bring up the second derivative test. And you're going to remove all of these, okay? We're going to come back to remove it. I'm going to bring you the second derivative test right in front of you. You can see how easy it is to use it. Okay, local max, local min. Okay. I will give you a closure, don't worry, okay? Now, second derivative test. All right, you look at second derivative test. Now we're going to tell about local max, local min. So I'm not going to use first derivative test, so delete. Okay, I have first derivative, so I'm going to follow second derivative test, right? So C is a critical number, right? C is a critical number, so I have two numbers. So first derivative at 1 is equal to 0, so that first condition is satisfied. Second derivative at 1 equals to, I'm just going to plug in the number. Okay, so that's going to be 12 times 1 minus 18. And that number is going to be negative. So the second derivative test, the first, the B applies, right? First order derivative equals 0. Second order derivative is negative. So what do we say? We say F has local max at 1. Okay, and then you say f of 1, you plug in number f of 1, you plug in, right, you get 2. Now, that's for first critical number. Second critical number, you're gonna do the same thing, right? So f prime of 2 is 0, and f double prime at 2 is equal to 12. I'm just going to plug in. You don't really need this piece, right? So 12 times 2 minus 18, this is a positive. So second derivative test A applies, right? Then you're going to tell the reader, hey, F has local minimum at 2. And of course, we already calculated, just plug in f of 2 is equals to 1. You're done. Okay, so if we do second derivative test to show work, and overall to answer this question, your work could be like this. Your work could be like this, right? You still have to do the first derivative test and give interval increasing, I'm sorry, you're not doing first derivative test. And but you still need to take first order derivative to answer the question of increasing, decreasing intervals. And but for local max, local min, you just apply second derivative test. And then concavity is all the same. Okay, I hope that clarifies. If you have any questions, please let me know. Thank you for watching.